this is about an extension proposal for BIDS for computational models, for storing the simulation results of computational models. And just a second. Okay, BIDS is an existing data standard, and widely used data standard, one could say, particularly for neuroimaging data. So it started out for neuroimaging data like MRI data, and later also other data modalities were added. And there exists an ecosystem of software products that can work with BIDS data. So this is an important advantage of having a standardized data format, that it is interoperable. So software products can read it, can use it, and it can be used to exchange data between different software products. And there exists already a number of BIDS apps. So typical neuroimaging software like SPM, Matrix, fMRI Prep, and so on, they all exist in the form of BIDS apps. So if the data is in BIDS format, these apps can directly read it and perform the typical processing on it. So reasons for data standards are that neuroimaging experiments produce complicated data in many modalities. We have so many different modalities, and every machine has their own format. And this makes it, of course, hard for different software developers or software products to understand all these different formats, to use them, to process them. And this leads to errors and wasted time, because everyone has to reinvent the wheel basically, and has to write importers again and again, and transformers for data models again and again. And while doing this, often errors creep in. And this is a problem for reproducibility, among other things, because if a data is standard, a data model is only loosely defined, then it's very easy that errors creep in. So for reproducibility, it is good if we have an exact description of inputs, the applied transformations, and the outputs that happen to a data set. And also its advantages for robustness, because a good structure makes it easier to detect errors. So for example, in BIDS, we have the BIDS validator. So when you have a BIDS data set, you can just run the validator over it, and the validator will then spot the errors, basically the formal errors, the structural errors at least. So for example, here we see that this MRI data set lacks information that would, when this MRI data set is then used in another project, lead to the problem that it cannot be processed accurately. If we don't know the phase encoding direction and the repetition time, then another one cannot use this data set. So we need to make sure that all this information is really there. And this is the nice thing about a data standard. We can then have validators, for example, or we can have programs that enforce structural validity. And this is necessary because an article about computational science is not the scholarship itself. It is merely the advertising of the scholarship. The actual scholarship is the complete software development and a complete set of instructions which generated the figures. So not the beautiful figures, which no one can reproduce after 1 month later, are the output of the research, but it is everything that is needed to produce these figures. And often exactly this is what is missing. So there's a cool Nature publication and it looks great, but then no one can reproduce it. And this is basically a null result then, because it cannot be used by anyone else. So BIDS in a nutshell. BIDS started out, when it started, we found it quite intuitive, because it was how we also organized our data. So when we did MRI experiments, then what you get back is you get such a DICOM directory. No one can understand what is meant by these files. So the first step usually that you do after you scanned your subjects is that you sort and organize the data into a format where other people can understand what is actually, and yourself can understand what is actually in there. So here, for example, we divide it into anatomical, functional, and diffusion weighted data. And also we divide it per different subjects, for example, in different sessions. And we also have already some metadata there that describes what these subjects characterize. And this is a common pattern in all in the BIDS standard. So BIDS standard is characterized by a directory structure. So we always have this division into subjects and also into sessions. Then we have a file name structure. So we have these key value pairs. So for example, here the task is REST. And also we have file name extensions to characterize what type of data is in there. So here it is bold data. fMRI could also have other contrasts, for example. Then we have JSON metadata sidecars. So the metadata like repetition time and all kinds of information that characterize a data set are then stored in these sidecar files that have the same file name, but only the suffix, the file name extension, is a different one. It's JSON because we can store structured data. Here's a larger example. So here we have already several different functional data sets. So for example, here we have bold data, we have events, we have also a physiological recording, maybe a heartbeat or something. We have also a reference image in the same modality space. So with these suffixes, then we can distinguish different data types of the same high-level modality, one could say. And also we have here already some code and also a folder for derivatives, for example, and also a description of the data set and of the participants, and also some generic descriptions about the data set. So the general file types in BIDS are, as it started out, were the imaging files, like Nifty files. Then we have tabular files, really just TSV files, basically. So this can contain any alphanumeric value, basically, in the form of a table. So we can write vectors or matrices into such a file, data vectors or data matrices. And then we have JSON files to specify key and value pairs, to specify metadata that characterizes the data. And as Petra already mentioned in the Princeton meeting, two broad classes of extensions were identified that would be needed. An explicit description of the input and output data for various classes of models, and a model-specific language that thoroughly or exhaustively characterizes the model structure. So also the physical understanding of the model. And this has, of course, the big advantage that when we have a generic description of the model, then we can automatically implement it in other software environments, which is a good way to check the reproducibility of a result, because often reproducibility depends on specific algorithmic choices or implementational choices. And this is therefore good. And of course, a problem with this is that we need to balance expressivity against simplicity. So there's always the problem if we want to address all use cases, then what we produce is too complex to be usable in the end. And so we need to somehow strike a balance. There's often the Pareto rule, the 80-20 rule used. And this is basically the same problem now from a slightly different perspective. So this can be observed with all kinds of standards. So be it digital standards or also like analog hardware standards. If there are 14 competing standards, then someone will identify this as a problem and will say, ridiculous, we need to develop one universal standard that covers everyone's use cases. And the end result of this will be that there is not one magic standard that covers everyone's use cases, but in the end there will be 15 standards. And this standard proliferation just happens. So this is a natural drift, basically, that things get extended and get more complicated until they are unusable. So for example, when with computational models, we would now try to pack all the key value pairs that characterize, or all the parameters that characterize a computational model into the file name, then the file name would be this long, and this is too long for a computer. So we need to exhaustively specify the parameters in sidecar files. We cannot put them all into the file name, basically. And also, it's good if we don't invent too many different file types, because this overcomplicates things again and makes it again hard to implement transformers, and also it's not necessary, basically, often. So it would be desired to avoid over-specialization, to not end up again with many different file types and key value pairs and substandards and so on, because this defies the whole purpose of a standard. And also a desired would be if there are already supports for reproducibility. So an explicit specification of the mathematical equations, the concepts, the software environment, and everything is needed. So the typical observation from computational science is that everything breaks down at a minuscule detail. So everyone tries their best to document everything, to implement in a reproducible way, but there will be one small detail that will lead to the situation that some person, some PhD student or postdoc will sit 1 week or 2 weeks or 1 month wondering what's this specific parameter value or this specific choice was in order to reproduce the result. Version control is also related to this, and provenance tracking. So we really need to understand every minuscule detail that happened to a data set from its inception up to the final figure. We need to track the whole history of what happened, where it happened, probably by whom also, and so on. Derived from these observations, we can formulate some principles, like it's good to have simple and generic data types and formats. So instead of tuning everything again towards specific software products and frameworks, it's better to, if we have something in a very generic and simple way, such that new software can easily adapt to an existing standard, right? So it's better if we have a standard, and if someone develops someone new, then they adapt to the standard instead of defining a new standard. And short file names are a requirement for computational models. So instead of putting everything and everything unnecessary in the file name, just put into the file name what is really necessary, what is really the distinguishing characteristic of this particular simulation result that distinguishes it from other results and that are important for the research. Then a domain-independent language to describe mathematical models of physical systems, also with a physical interpretation, would be great. This is often needed. So the verbal description of a model in a paper is mostly not sufficient to really understand every logic and every computational, implementational choice behind it. So we need a machine-readable, a machine-understandable description of the model that comes with the scientific output. And also, the data model can be agnostic of the metadata. So this is really about specifying the data. So when we hear, what we here call metadata is something that's specific, that is data about the data model. So it's metadata about a data model. It's not metadata about the scientific interpretation of what's in there. For that, we can again map other standards. So here we can pick our ontology of choice and just map them onto the data again. And there it's all again helpful if the data standard is relatively simple. So having these considerations, one could define a small number of data types. So what we really need is we need to somehow define the space and the time in which we live. So we have the spatial and temporal coordinate systems that we somehow need to define. Then every computational model, a computational network model, probably one should say network model, needs a network graph description. So this is not maybe this extension is not about generally computational models, but it's about network models. So which is the prominent or the most important probably class of computational models here. If we have time, space, we have our network, and then we can store the outputs of a simulation mostly in a very simple fashion. So the outputs of a simulation are usually time series. It's a dynamic model, so the most important output is the change of the model over time, of the model dynamics, and derived from that, everything that is not temporal can be called spatial. So we need something to store temporal objects, we need something to store spatial objects, and lastly, what is needed is the logic, the understanding what produced all of this, and these are the mathematical equations and the physical interpretation. And then really the last ingredient is then the computer code. So having all of this is nice, but without the computer code, it's still hard to reproduce a result. And often the result depends on the computer code. So we also need the computer code for full reproducibility. The nice thing is most of this, almost all of this can be done with TSV and JSON files. For representing the mathematical equations, LEMS or NeuroML offers itself, and this is currently specified using XML. It's very similar to JSON. And then computer code is harder to standardize, but their containerization is helpful. And now we can really look at the already existing specification extension, basically. So the specification is implemented in the form of YAML files and markup files, and from there automatically the specification is then compiled in the form of here websites or PDF files, and there the whole knowledge necessary to use the specification is contained. And we have, for example, some common principles. We mentioned it already. What is a data set, for subject, session, and so on. These common principles appear over and over again in all BIDS modalities and extensions. And here now we are talking about the computational model extensions. As we can see here, we have already several modality-specific files like genetic descriptors, PET data, behavioral experiments, and so on. And computational models is then one of these modality-specific files for BIDS. Okay, and as we said already, we could store all these data using simple file types, network graphs, mathematical equations. So we basically would sort these data then in different folders. So this is the message here. For all of these different data types, we have one folder. So for the graphs, we have the folder net. For the equations, the folder equations. For the parameters, the folder params. So this is to distinguish equations. Basically, often you have one model or maybe two models, a slight variant of the first model, or maybe three variants or so on. So we have our three variants neatly stored in the folder equation. So we can see, okay, in this work, which produced 3 million simulation outputs, three model variants were used. And then in the folder parameter, we can then specify for each individual simulation results the small set of parameters that was indeed varied or actually varied for a particular output. So we have our 3 or 4 different model variants in the equations folder, and then we have 3 million files with parameters in the param folder, where for every simulation output file, we have the parameter set. And together, the equation in the parameter file then constitutes the computational model. And this is using the language LEMS. So TVB, for example, has already an interpreter. So TVB can already read LEMS, or in TVB it's called RateML, specified models and simulate them. Then a folder computer code to store the computer code, and then a folder for the time series output. So every time series is so either just a vector or a matrix, basically. Everything that's not a time series is then a spatial object, like, for example, a functional connectivity matrix, a power spectrum, or something else. Then in order to align time series, spatial objects, and networks in a common reference space, we need coordinates to define, to annotate their alignment in a coordinate system. And all of this can be done with 3 or 4 file types, basically. So as we mentioned already, for every output, we need to know where and when it is. So a mandatory metadata field for every file, every data file, every time series, and every spatial object is to specify the coordinates of the rows and the columns. So remember, we have data files, right? So these are TSV files where we have either a vector or a matrix. And so we have rows and we have columns. So for each column and for each row, we want to know exactly where this entry is aligned in a coordinate system. So for each row and for each column, we have a coordinate. So these coordinates are also stored in TSV files, and they also have themselves metadata that specifies them. Of course, coordinates, the metadata for a coordinate is, for example, the unit. This is we need to know which unit a coordinate has. Otherwise, we don't know where it is in a coordinate system. So units can be, for example, seconds or meters, and so on. So for example, if the first time step in the first line, row 1 of a time series file, if we want to know at which point in time this happened, then we would look in the linked coordinate file which specifies times. So one coordinate file, for example, specifies times. Times can also be specified in a simpler way. If the sampling is equidistant, then the time can also be specified using sampling rates or sampling delays. But if it's the case that we only want to look at a specific range, it's often useful if we specifically say this started at time point 321 and goes until time 400. Okay. And these are all the types of coordinates that we can have. We can have, for example, times. We can have the nodes. So these are the locations of network node centers. So these are where is the neuron or the neural population in 3-dimensional space, basically. Then we can have vertices and faces as coordinates. So surface triangulations are often used to have 3D models of cortical surfaces, for example. So a coordinate is also the index of a vertex and the face, basically, that makes up a triangulation. We can also have normals, for example. These are all also coordinates, or labels. A label is also a coordinate, a textual identifier like prefrontal cortex or V1. Or a sensor is also a coordinate. Like this could be a Cartesian coordinate, or could also a sensor label. An area, a volume, a surface. These are also can also be coordinates. And if none of these matches your coordinates, then one can use generic Cartesian 2D or 3D or polar 2D or 3D coordinates. Network graphs then are characterized. So the neural networks are typically characterized by their strengths of interaction and by the time delay of interaction. And this can be defined, so at least the time delays can be defined in at least 3 different ways. So we can compute the time delay from the distance by dividing by transmission velocity, or we have delays or speeds. And weights, of course, or the strengths are an important descriptor of a network. There's a bit out of the order here. So this is coordinates metadata here. So metadata of coordinates are units, as we said already, but existing in BIDS already are other key value pairs, like, for example, anatomical landmark coordinates or the landmark coordinate system and coordinate units and so on that can be reused. So for example, if the coordinates are specified in terms of M&I space, for example, this is a concept that exists already in BIDS, so we can reuse this here and reference it here again. Time series data then can have so a simple file type, a TSV file, and there we can have different types again of time series. So the usual output of a simulation is the state variable, the dynamic of the state variable, so the extension or the suffix vars specifies state variables. Then we can have stimulation time series. So stimuli could be the extension here. We can have noise time series. Often it's not sufficient to store the random number seed generator in order to reproduce a result, but it is really necessary to really store the explicit noise time series. So this could be done here, for example. We can also store spikes in a raster format, which is not so efficient, or in a sparse format. We can also store empirical time series, although I'm not so sure whether this should stay there, because there are also other extensions of the BIDS where this is potentially captured, but this is not decided yet. Then if none of this matches our use case, then TS is a generic time series container, and we can also store events or labels, annotations that happen at this particular time points using this events extension. If 3D objects, if 2D objects are not sufficient, like vectors or matrices, like 2D objects like matrices are not sufficient, then we can serialize higher dimensional objects into series. So for example, if we have a series of temporal objects or a series of spatial objects, they can be grouped using this series keyword. And then the output of a simulation needs to be exhaustively annotated with metadata that characterizes the complete set of instructions that is necessary in order to produce this output. So we really need to know the model equations, the model parameters, the source code version, then the produced software. So source code is not enough. We also need to know which software, which particular build of this source code was used. So the software version, the software name, and the repository where it can be obtained. We need to know the network that was used to produce the result. And probably we can also add a sampling period, a sampling frequency if this was sampled at equidistant times. And spatial data is everything which is not a temporal object, like functional connectivity matrices and so on. Here again, we can use series to serialize higher dimensional spatial objects. And the metadata is largely similar for spatial objects as it is for temporal objects. So we need to exactly know equation parameter, source code, and the software and the network and the coordinates that were used to produce this result. Then equations, as we mentioned, have a special role because they use XML. This is the format is called LEMS, a low entropy model specification language, which is a high level language which should be able to express all physical systems, and yeah, which is basically used here. We can have a quick peek at how this looks like. So this is this is how the reduced Wang-Wang or dynamic mean field model in TVB it's called reduced Wang-Wang, and Gustav Deco and others call it dynamic mean field model, is implemented in LEMS. And here we can see, for example, we specify all the parameters that this model contains, like contains the parameter V plus, for example, and this is a constant along the whole simulation. It has the value 1.4, for example. And after defining all the parameters of the model, we then define the dynamics of the model by specifying the state variables and the dynamic equations, the ordinary differential equations, or the dynamical system that specifies the model, basically. And these are here the equations, basically specified as a text string referencing all the parameters that were defined beforehand. And for LAMs already, there exists an ecosystem of parsers, readers, simulators, like PyLAMs, for example. And as mentioned, TBB also supports LAMs, and one can simulate models directly in TBB with LAMs. And the equations then are linked again to a source code that implements these equations in the context of this research output, source code version, software version, software repository, and so on. So this is just a slide that compares NeuroML and LAMs. So LAMs can also be mapped to NeuroML, which is another language for specifying equations. So this is also good that these mappings exist and can be used to make reproducibility studies, for example. And we have model parameters, as we already mentioned. So this is a bit to disentangle equations from parameters to give a better, more intuitive, human-readable overview. What were the variants of the models that were used in this simulation? What is the parameter? So otherwise, one would have to skim through 3 million parameter files to find out which variant was used where. And computer code, it's hard to standardize, but with exhaustive metadata and the repository availability and ideally also containerization, it should also be added to the research output to make the result reproducible. Here again, the same metadata basically that specifies the must knows. And yeah, we are at the end already. So in summary, this is a BIDS-like data model for computational model simulation results based on simple and generic data types and exhaustive metadata annotation for reproducibility.